So now we're going to take a closer look at some of the common properties of longitudinal sound waves. First of all, why is sound wave a longitudinal wave? By definition, for longitudinal wave, the oscillation of the particles in the medium is along the same direction as the propagation of the wave. And that is exactly the case for a sound wave. Now, as we saw from the derivation of the wave equation for sound, we considered a column of air, or any medium for that matter. So we used the x direction to indicate the direction of propagation of sound. Okay, so I can draw this x direction. So this is the x direction. And as we saw in the derivation, we considered a slice of air in this column here, this slice. And then we looked at how the left edge moved and how the right edge moved. And the motion obviously was like this, right? Was like this. It was denoted by S as the displacement. So as the particles of air oscillate along the x direction, this is the x direction, the wave also propagates along the x direction. So clearly, this is a case of a longitudinal wave where both the oscillation and the propagation happen along the same direction, which in this case is the x-axis. This is to be differentiated from the case of wave on a string, where if you look at the length of the string, we call that direction the x direction. The oscillation of the string is in fact perpendicular to it, which we call the y direction. Okay, so this is to say that sound wave is indeed a longitudinal wave. Now, let's look at some examples of the speed of sound. The speed of sound, the general formula, as we saw in the previous lecture, was given by v equals to the square root of b over rho. B is the bulk modulus, and rho is the density of the medium. Perhaps the single most important example of the speed of sound is that in air, because we humans live in air, and we listen to the sound in air, so we really need to know the speed of sound in air. Air is a gas, and gases can easily be compressed, relatively speaking. Now, as you compress a certain amount of gas, you have to exert a pressure. The greater the amount of pressure you need to exert to cause the same amount of compression, then the greater the bulk modulus, right? Or we can say the stronger, the more resilient this material is. Now, consider a tank of gas, okay? If I want to compress the gas, I wonder how hard it is to compress the gas. How much extra pressure do I need to exert in order to compress the gas? Well, the answer to that depends on the property of the gas, the state of the gas. Is it really under a lot of pressure already? See, if the gas is under a lot of pressure, then it is really hard for me to make it even smaller, right? To compress, right? But on the other hand, if the gas has very low pressure, then it's easy to get it compressed. So the bulk modulus for gas depends on the pressure. You can expect that a greater pressure in a gas leads to a greater value of the bulk modulus. Okay, so it can vary a great deal, even for the same gas. If you change the pressure, you can get a very different value of bulk modulus. This is to be differentiated from a solid matter such as steel. Okay, so how does one calculate the bulk modulus for air? Well, we're going to see some more details in the calculation when we study thermal physics. But I can tell you that you can borrow this formula for now, and that is B is proportional to the pressure of the gas, which, as we see, makes sense, but it is not equal to the pressure of the gas, which we call P naught. There is also a constant in front of it, which we'll call gamma. Gamma depends on the molecular structure of the air, or more precisely, it depends on how many atoms are there in each air molecule. Well, air, as you know, is a mixture, but the predominant ingredients of air are nitrogen, oxygen, and these are both diatomic molecules. And for diatomic molecule, you will learn in thermal physics that gamma equals 1.40. Okay, you will see that later. And it makes sense that B is proportional to the air pressure P naught. I use P naught, not P, P naught is the ambient pressure. I mean, the actual pressure is P naught plus delta P, but delta P is a tiny, tiny addition to the overall pressure, even though delta P is what's responsible for the sound that we hear. Okay, so let's consider STP. Okay, at STP, standard temperature and pressure. That's what STP stands for. Okay, P naught is 1 atm, right? 1 atm. It is also equal to 1.015 times 10 to the 5 Pascal. Okay, now as we know, the bulk modulus is measured in Pascal or Newton per meter squared, and the pressure is also measured as Newton per meter squared or Pascal, so it makes sense. They're proportional to each other. Okay, now, so we have this. We have the value of gamma and P naught for the bulk to calculate the bulk modulus for air. What about the density? Well, under STP, the density of air is 1.29 kilograms per meter cubed. Okay, so with all the numerical values, then we can calculate the speed of sound in air. So in air, it is equal to the square root of gamma P naught over rho. And we can plug in all the numerical values, and let's see what we come up with. So we get 1.40 times 1.015 times 10 to the 5, okay, in SI, prime SI units, divided by the density, which is 1.29. And if you do the numerical calculation, you come up with 331 meters per second. That's according to our theory. Does that agree with experiment? Yes, yes it does. All three sig figures match precisely the experimental value, at least to the first three sig figures. So our theory is highly accurate. Okay, now this is under STP, okay, standard temperature and pressure. So the temperature is 0 degrees Celsius, pressure is 1 atm. So that's the pressure at sea level at that temperature. But as the temperature changes, you can expect the speed of sound in air to change as well. If everything else being the same, if you increase the temperature, then you can also increase the pressure. I mean, that's common sense. And you will see that more precisely when we study thermal physics. Basically, each air molecule on average move faster as the temperature rises. So they're going to create greater amount of pressure, and therefore it's going to be harder to compress a hot tank of gas versus a cold tank of gas. And so that means that the speed of sound in air will increase as temperature rises. Okay, and that's our theory. And does it agree with experiment? The answer is yes as well. You will learn after we study thermal physics, we'll get to know how pressure changes as temperature rises. And once we have this precise relationship, you will find that there is a correction to the 331 meters per second, which is only valid at STP, so that when the temperature is higher or lower than that, you have a general expression for the speed of sound in air, which is now a function of temperature. And I can write down the formula for you. You will see the details in a later chapter in thermal physics. It is equal to 331 meters per second times a corrective factor due to the temperature change. And that corrective factor is 1 plus the temperature of the air in Celsius divided by 273. Okay, so for example, if the temperature is 0 degrees Celsius, in other words, Tc is 0, then it's just 331 meters per second. What if the temperature is 30 degrees Celsius? Then you don't just have 331 meters per second, you have to multiply this by a corrective factor, and that factor is 1 plus 30 over 273. Okay, so the higher the temperature, the faster the air the speed of sound is. And you know that makes sense not just from the pressure point of view, but also from from the microscopic point of view. Think about the air molecules. The air molecules moving around, they are the ones responsible for sound, right? And if they move faster, then of course they can communicate with each other faster, they can collide with each other faster, and therefore they can propagate the signal of the sound faster. And that happens at higher temperature, of course. The higher the temperature, the faster they move on average. Okay, so quantitatively it makes sense. Now, let's take a look at another example of the speed of sound. What about the speed of sound in water? Okay, let's try to use the same formula, square root of b over rho, and let's see how we can find the speed of sound in water, and let's see how it compares with experiment. Okay, in water. Now this time, we cannot quite calculate the bulk modulus from theory. It's more complicated than that. So I'll just have to give it to you. So B, the bulk modulus for water is 2.1 gigapascal, so 10 to the 9 Pascal. And you notice that it is much greater than the bulk modulus of air, which makes sense because, you know, and I mean, have you ever tried to compress water? It's nearly impossible, right? You compress air, it's much easier, right? So because the bulk modulus of water is much greater, it's, you know, it's more than 4 orders of magnitude greater than that of air. So it makes sense. All right, but the density is also higher. Density of water it's not quite 1.29, rather it's about 1,000, right? Kilograms per meter cubed. It is 1 gram per centimeter cubed. It's also 1,000 kilograms per meter cubed. So you have greater B and also a greater rho at the same time. So look at the ratio of B over rho, and you take a square root. Then you will get V water, the speed of sound in water. And what is that equal to? It is equal to the square root of 2.1 times 10 to the 9 divided by 1,000 kilograms per meters cubed. And if you do the math, you'll find the answer to be, to the first two sig figures, 1.4 times 10 to the 3 meters per second. So sound travels faster in water than in air. The speed is about 1,400 meters per second, or 1.4 kilometers per second, just a little under 1 mile per second. Okay, now, again, the speed of sound is determined by a pair of parameters, the elastic modulus and the inertia parameter, which is usually either the three-dimensional density rho or the linear mass density mu, if it's the speed of the wave on a string. In our case, if you compare water with air, the bulk modulus and the density both are greater, but the bulk modulus increase by a greater factor than the density increases. So overall, it's more elastic because of the strong connection, elastic connection between the water molecules compared with the looser connection between the air molecules. And that's how the signal, the wave signal can propagate faster in water than in air, right? So that's the theoretical value. What is the actual value? The actual value measured is 1,433 meters per second, the experimental. Wow, look at how close we are. We got the exact same value up to the first two sig figures. All right, so our theory really works, and you can check out other materials as well, but I want to caution you that for gas and liquid, there is only one speed of the speed of sound. If you go to solid, such as steel, things are more complicated. You will find, if you do some research, you'll find there are several values of the speed of sound. It depends on in which direction it propagates. It's more complicated than that. We don't want to get too far into this, but if you look at a uniform liquid or uniform gas, such as water or air, you know, our formula is equal to B over rho, work very well, as you can see. All right. Now, let's take a look at the general solution to the wave equation that we just obtained. We know, we found what V is, right? By comparing this wave equation with the standard equation we saw from the previous chapter, right? For the wave on the string, they assume the same general expression. We, in fact, found this general solution to that equation. It turns out to be any differentiable function f, as long as x and t are linked together. The general solution back then was any function f, differentiable function, of course, x plus or minus vt. As long as x and t are related like that, then you can take that x plus or minus vt and plug into any differentiable function f. This will constitute a solution. The same thing happens here because it's exactly the same equation. Okay, just replace, s with y with s. That's it. Okay, so s as a function of x and t equals this. That's the general solution. Now, I've never seen any common differential equation whose solution is so general. Usually, you give me a differential equation, the solution usually is special to that particular equation. For example, some equations have sine and cosine solutions. Okay, as you saw, it's simple harmonic motion. But if you put a tangent, it doesn't work, right? It's not a solution. Or we put an exponential, it's not a solution, right? But in this case, you can put any differentiable function in it, and they all satisfy this equation. I mean, you don't have to believe me. You can review what we derived in chapter 16, or you can start from scratch and do your own derivation. The way you do that, as you saw in chapter 16, just define a new variable u, which is equal to x plus minus bt, and then you do the derivative. Okay, you differentiate twice on both sides, left and right side, to get a second derivative, and they will match. Okay, they will match. So it works very well. Now, that is very important, the fact that the solution is so general, because it tells us that this equation can support pretty much any waveform. We're not limited to sine, cosine, or exponential, any differentiable function. The wave can assume any shape. That is the beauty of the solution. Okay, and the plus or minus sign is such that when you use a negative sign here, so x minus vt, then the wave propagates along the positive x direction. Okay, that is it's because when t increases, you have to increase x to keep the argument x minus vt equal, which means if there's a crest at a certain position, as t increases, x has to increase to keep x minus vt the same, so you keep the same crest. Because the crest will move along the positive x direction. On the other hand, if you use x plus vt, then it's the same as reversing the sign in front of this velocity, so it's going to go backwards. Okay, along the negative x direction. The same as we saw in the previous chapter. Okay, so that is the general solution, but we are going to be more concerned about what we really deal with when it comes to acoustics. And now when you listen to music, you hear different notes, right? What is the difference between a C and an F, for example? Well, the primary difference is the frequency. Okay, now frequency is a concept that is only valid for a periodic wave. It's just how many times it repeats itself every second. That's frequency. Not all waves, not all sound waves are periodic. Some sound waves are not, but we're mostly going to be concerned about periodic sound waves. Okay, and even within periodic sound waves, not all sound waves assume sine or cosine dependency of space and time. In other words, there are sinusoidal sound waves and there are non-sinusoidal sound waves. Both can be periodic, right? So you can think of a periodic wave, for example. Let me draw a periodic wave. It may look like this. It may look like this, right? So certainly repeat itself, but it doesn't look like a sine or cosine function. But it turns out that there is a tool in math called Fourier Analysis. And what it tells us is that for any periodic function, you can always break it down to a bunch of sinusoidal functions, a bunch of sine and cosine functions. Okay? And if you only have one term, one sine, cosine, and one cosine function, then it becomes a sinusoidal wave. So think of sinusoidal wave at the most basic periodic waves. So if we can understand how a sinusoidal wave behaves, we can understand how all periodic functions, periodic waves behave. There's a mathematical basis for that. Okay, so it's not just a periodic wave, it's a sine cosine wave. So it looks like this, okay? It looks like this. And as we saw from the previous chapter, we have all the same definitions here. This is the wavelengths. Okay, this direction is what we're plotting along the x direction. Okay, so here's the x axis. Okay, and so this is how the wave repeats itself in space from one crest to the next crest. The distance is called a wavelength. Okay, And if the frequency is f, then we know that lambda equals v over f. It's the same situation we saw from the previous chapter. Okay, so now let's focus on sinusoidal sound waves and look at some features of that. So we have some plot for both the pressure variation and displacement of air molecules for a sinusoidal sound wave. Okay, so you have a speaker producing sound. The left side of this plot is for delta P, and that is the pressure variation caused by sound. The right side is a plot of displacement. The air molecules move back and forth, causing a pressure variation. So of course they're related, but if you take a closer look, you'll find that one is sine function, the other is the cosine function. Okay, see, here's a sine function, but over there is a cosine function. See that? So that tells me that when there is a peak of the pressure variation, it's not the same position as the peak of the displacement. Okay, in fact, when sine is maximum, cosine is actually 0, and vice versa. Why is that? Well, mathematically we can see why, because we saw in our first lecture when we derived one of the two equations leading to the equation of the sound wave, we saw that there was a connection between the pressure variation delta P and the displacement S. Right? And here's that connection that we saw. Okay, here's that connection. So you see, delta P is not proportional to S. It is proportional to partial S over partial X, the derivative of S with respect to space. That is why if you plug in S as a sine function, then you take a derivative, aren't you going to get a cosine function for delta P, right? So mathematically, it makes total sense. But what's the physics behind it? How come one is sine, the other cosine? How come they're not in phase? How come the peak of displacement is not the same location as the peak of the pressure? Well, this can easily be understood if you look at how the pressure actually varies. Normally, the pressure is just P naught if there is no wave-like movement of the air molecules. Okay, if they only move randomly, then the density is always the same everywhere. The air is neither getting compressed nor getting decompressed anywhere. So the pressure is even. Okay, now the pressure increases when the density of the air is higher in that region, meaning that the air molecules are coming towards and they get congregated in that region, and that increases the density of the air molecules there, which in turn increases the pressure. Okay, and if for another region, if the air molecules are moving away from that region, the density drops below average and the pressure also drops below average. So if we consider a segment of the air, okay, consider segment of the air, this segment here. So this is at location X, and that's the location X plus dx. Okay, if we consider what's going on here. As you know, if the sound propagates along the X direction like this, if the sound propagates like this, then air molecules will be moving also along the X direction, back and forth, right? Back and forth, along the X direction. Suppose the left edge moves by an amount S. The right edge also moves by an amount S. So this is S, this is also S. Then is there any net change in the volume of this region? Okay, the volume of this region here. Well, the answer is no, right? You still have the same region. The reason why the volume changes is because the left edge and right edge moves by a different amount. So here is S, the right side is S plus ds, okay? S plus ds. And that is the reason why, this region can either get compressed or decompressed. For example, if ds is positive, then the right side moves more than the left-hand side, therefore the volume increases, so this region gets decompressed, the air pressure will go down. And if delta ds is negative, that means overall the volume shrinks, and therefore there's a compression, so the pressure rises, right? So the reason why there is an additional pressure delta P is because the left and right side move by different amount. Okay, so you're not looking at S, because S and S can cancel out. You're looking at ds. When ds is large, you're going to get a large amount of compression or decompression, leading to a large change in the volume of the region, therefore leading to a greater amount of pressure variation, which is delta P. This is the reason why delta P is not proportional to S, but proportional to the change in S. So ds over dx, that's ds over dx. Okay, but of course we're going to use partial derivative because I'm assuming this picture is taken at the same moment. So both left and right side has the same moment t. Okay, so that's why. That's why if you're looking at S and delta P, they're not proportional to each other. Okay, the greater the change in S as you move along the x-axis, the greater the change in volume for that region of air, and therefore the greater amount of pressure variation delta P you're going to get. And it is this reason why when you have a zero change delta S, partial S over partial X, this is a region where the left and right side, the left and right edges of this block of air move by the same amount. So therefore, there's no volume change, and therefore there's no change in pressure. Delta P becomes 0, and that's exactly what happens at, for example, this location. Let me highlight it for you. At this location, where partial S, partial X equals 0. Okay, this location right here. Right, S does not change as you move along the X direction, and in a corresponding location, there's no P. So P is 0. Okay. Now over here, look at a different position. I'm looking at a different position. So over here, you have the steepest change in S as you move along the X direction. Okay. And this is where the pressure is a peak. That's the pressure right here. See that? Whether it's positive or negative doesn't matter. But it has the greatest deviation. The pressure has the greatest deviation from the mean value of P naught. Okay, so that's the physics. You can understand why delta P is proportional to partial S, partial X, not to S itself. All right. And we are going to continue our discussion of the general properties of sound wave. And in the next lecture, we're going to focus on the power and intensity of a sound wave, leading to the concept of sound level measured into so-called dB or decibel. We'll see that in the next lecture.